Hi. Hello. Good afternoon to everybody. Okay, welcome to the new session of the Valongo seminar. Okay, I think we can start today. We have the pleasure to host Dr. Ilse Looze from Ghent University. Just to give a short presentation, Dr. Ilse Looze got her bachelor, master, and PhD at Ghent University. Then she was awarded a FWO fellowship, always at Ghent University, and she spent part of this fellowship at Cambridge University. Then she moved to London at the University College as a postdoc, and she stayed there for 2 years. Then she moved back to Ghent, again with another FWO fellowship. Until in 2020, she was she became professor at the University of Ghent, and Dr. Ilse Looze has a very wide range of interests in extragalactic astronomy, including dust production supernovas that we probably see today. But she also worked in studying dust composition of galaxies. She's worked with the low metallicity galaxies, star formation rate calibrators. She published more than 100 papers, and in 2020 she was awarded a European Research Council grant, whose name is Dust Origin, and the title suggests that the scientific objective of this project will be to study the origins of dust in galaxies. So Ilse, thank you very much for accepting this invitation. You're very busy, so we have to finish at 3 sharp, unfortunately. So please go on, and then I'll come back after you finish. Thank you very much, and welcome to the seminar of Valongo.
Thank you very much, Marco, for the introduction, and thank you very much for inviting me to give this talk today. Can you hear me okay? I'm assuming you are. So today, okay, perfect. Today I want to briefly talk to you about the origin of dust problem in galaxies, and specifically about the competition between supernova dust formation, interstellar dust growth, and dust destruction processes in nearby galaxies. So let me start with a brief introduction for people not working on dust every day. So the interstellar medium, we know it's not completely empty. So the space in between stars and gas is actually made up of low density gas and microscopic dust particles. So more or less by mass, the ISM consists of about 70% of hydrogen, 28% of helium, and then a smaller fraction of heavier elements. And about 1% of the mass of the interstellar medium is composed of the interstellar dust. So you can call them solid particles made out of metals. Now, just to give you an idea how low density the ISM actually is. So imagine you take a pint and you fill it with atmospheric air at sea level, then it would contain about 5 times 10 to the 22 particles. Now imagine that you take the same pint into the interstellar medium of a galaxy and you would fill it with ISM material, then it would contain only about 500 particles, assuming an average ISM density, so significantly lower than the typical densities that we're used to of the air here on Earth. Interstellar dust, you can consider it broadly as being somewhat larger molecules consisting of several atoms, with the smaller ones having about 10 atoms or so, and the largest ones consisting easily of 1 million atoms, with sizes that range between 0.01 and about 20 microns. And we broadly distinguish between 2 different compositions. We have the carbonaceous grains and then the silicate type of grains. Of course, there are many more varieties, but just to give you a broad idea. You may wonder, why should we care about dust if it's such a small component of the interstellar medium? Well, we know that it obscures a lot of the starlight, and especially of young stars. So broadly of a galaxy, it's gonna extinguish about 30% of all stellar light. We know it's also enhancing star formation because it provides an important coolant in dense clouds, enabling them to collapse. It can also provide the fuel because on the surfaces of dust grains, hydrogen atoms can meet and form molecular hydrogen. And we've come to realize recently that also radiation pressure on dust grains can actually play an important role in driving galactic outflows. Now, just to give you a brief overview of what are the important dust sources and sinks. So for a long time, we've known that low and intermediate mass stars produce dust when they go to their asymptotic giant branch phase. So when they puff up to be giants, their outer envelopes can cool down significantly, and you can get dust condensation taking place in these outer envelopes. Then with supernova 1987A going off more than 30 years ago, people also started to realize that actually more massive stars, so after they explode as a supernova, have a lot of metals present in their ejecta and can form dust as well. And then there's a non-stellar dust production source called grain growth, and there it assumes that you have some grain seeds coming from some of these stellar sources, but that you have elements present in the gas phase as well, which gradually accrete onto these pre-existing grain seeds and grow bigger grains like that. I'll come back to that later on. It's still somewhat controversial. And then broadly, the two most important dust destruction sources are, on the one hand, astration. So imagine you have a gas cloud collapsing to form a new star. Then some of the dust that is present in the gas cloud will also be incorporated into the new stars. And then a very important dust destruction source are also supernova shocks. So when a supernova goes off, it's sweeping up a lot of interstellar material, and it's destroying some of the dust on its way. Now, what is the origin of dust problem? So typically when people try to estimate what the dust mass is in a galaxy, typically from looking at far infrared to millimeter data and constraining the emission of the dust spectral energy distribution, and if they compare it to stellar dust production sources, then they find that it's insufficient to account for the observed dust masses, and that we would require about 90% of all the dust to have grown in the interstellar medium. So not through the stellar sources, but really grown through accretion of elements onto pre-existing grain seeds. Now, there are a few observational trends that have led people to argue for grain growth. And one of those is shown here. So you have the trend with the metallicity on the x-axis, and on the y-axis you see the dust-to-gas ratio. And you can clearly tell in both plots that when you're at very low metallicity, so at the bottom left of the panel, you have a very low dust-to-gas ratio, and then it actually really very quickly shoots up to have very high dust-to-gas ratio when you go to about solar metallicity. And people have argued that it's actually due to grain growth, because grain growth is very much dependent on how many metals or elements you have present in the gas phase. So that's one argument that people have used, in addition to, for instance, dust depletion trends, and I'll get back to that later. Now, the problem a little bit with these kind of studies is that people try to tweak some model parameters, and they typically do a by-eye fit. So for instance, you can see an example here of the best fitting models that were found on the left-hand side, so to reproduce the observed trends there. And you can see that they reproduce trends with very increased levels of grain growth and very low supernova dust production yields. Now, there are a few caveats. First of all, supernova dust yields are highly uncertain, and I'll come back to that later, showing you a graph of how uncertain they are exactly. One aspect is that we don't know what kind of grains actually condense in supernova remnants, so that makes the dust mass uncertain already by a factor of 4 or so, because we have to assume some dust opacity to go to a dust mass. On the other hand, we also don't know how much of the freshly condensed dust in supernova remnants will actually survive the reverse shock. So what happens if you have a forward shock and it's sweeping up a lot of interstellar material, then at some point it will get a rebound, and you'll get a reverse shock that is propagating inwards. And this reverse shock can actually destroy quite a lot of the freshly condensed supernova dust. For instance, in Cassiopeia A, it's estimated to destroy about 70% of all the dust. Now, whether grain growth provides a viable mechanism remains to be seen, because what people typically find, they haven't found a physical mechanism yet to actually grow grains in the interstellar medium. If you go to a very diffuse medium with low density, the accretion rate is expected to be lower, because typically you'll have fewer chances of an element that is going to hit the surface of a dust grain. If you go to more dense media, the problem is that you'll start forming ice mantles, and everything that accretes onto that will be removed as soon as it's exposed to UV radiation. So it's definitely a problem that remains. In laboratory experiments, people have shown that you can grow grains, but of course that's under idealized conditions, and we don't know whether it actually takes place in the interstellar medium. Another important caveat is that currently our dust destruction estimates come from the fact that we do models where a supernova goes off in a homogeneous medium, and we actually know in the interstellar medium that you constantly have clumpy filamentary structures, so it's not very realistic at all. And people have argued, doing some simple calculations without doing the proper modeling, that actually taking into account this 3D filamentary structure, the dust destruction efficiency may actually be lower. So typically with these highly efficient dust destruction efficiencies, you get dust lifetimes of about 100 million years, which is quite short, because that means that you have to replenish your entire dust population on a timescale of 100 million years. Another problem is that galaxy dust masses have been overestimated in the past. So in the graph on the bottom right, you see 3 different dust models with the same level of dust mass. So for the same dust mass, how much would they emit? You can clearly see that the blue model and the green model are a lot more emissive than, for instance, the Drain and Lee model, which has been frequently used. So we think that dust masses have been overestimated by a factor of 2 or possibly even more. And then the other problem were the by-eye fits, which I've shown you before in this previous slide. So we've tried to overcome some of these caveats in our recent work. So what we've done is we've used updated dust models using the blue model, which you can see here, so the Themis dust model. So our dust masses are lower by a factor of 2 on average compared to before. And we've also done a rigorous search of the full parameter space for the first time. So no by eye fitting, but really trying to see, okay, if we look at the multidimensional parameter space, what are now actually the solutions that could work and that could reproduce the scaling relations for dust, metals, and gas that we observe in nearby galaxies. So we gathered a total sample of more than 400 nearby galaxies, where we required them to have H1 mass measurements. You can see that we cover a wide range in stellar mass, specific star formation rate, H1 mass, also somewhat a narrow range in metallicity. So most of the galaxies are biased to be around solar metallicity. We do have a few lower metallicity galaxies, but it's quite restricted. Then what we've done is we've constructed scaling relations. So on the x-axis, you always see the H1 over stellar mass ratio, because we found all the properties that we show here, the stellar mass, the metallicity, the dust to stellar mass ratio, the dust to metal ratio, all really nicely correlate with the H1 over stellar mass ratio. And we use the H1 over stellar mass ratio sort of as a proxy for how evolved a galaxy is. So you can imagine a galaxy starts off with a lot of H1 gas and very little stellar mass. So it starts off on the right-hand side of these diagrams and gradually moves to the left when it's consuming more and more H1 gas, more and more gas, and is forming more and more stars. So you can see them as sort of evolutionary trends. So what we've done is we've used a new dust evolution code, DEUS, which stands for Dust and Element Evolution Models. And we've coupled it to a Bayesian Monte Carlo Markov chain framework to really do a rigorous search and efficient search of parameter space. Sorry. So as model inputs, we require a star formation history. Then we have some theoretical inputs. So we have to assume initial mass function. We have to assume some stellar metal and dust yields. And the same for supernova, metal and dust yields. And then we have to make some assumptions about gas infall and outflows. Then we have a series of model constraints, which you can see in the purple box. And I've shown you also in these scaling relations. Sorry. And then we have a few free DEUS parameters, and I'll come back to that later. And the output that we get is actually these corner plots, as we shown on the right-hand side, where you can nicely tell for each of the parameters what their probability distribution function is from the plot on the top of each column. And then you can also see in the contour plots what is actually the relation or correlation between two parameters. Now, what we've done for these 6 evolutionary bins, so let me go briefly back. So bin 1 starts on the right-hand side, so corresponding to the least evolved galaxies, and gradually moving to the red bin, so the leftmost bin, with very evolved galaxies, which have high stellar mass, but very little H1 gas left for future star formation. So what we've done is because typically in studies, what people do is they assume a fixed star formation history, and a very popular one is shown in red is the delayed star formation history model. So we wanted to take a step back and try to derive a customized star formation history. So you can see, for instance, for the least evolved galaxies in bin 1, you can see that they were not forming a lot of stars in the past, when we look back, but they gradually really start forming more and more stars recently, with a peak during the last 10 million years or so. And we did the same using different tracers of star formation for the other galaxy bins. And you can see, for instance, for bin 6, the most evolved galaxies, that we clearly have formed most stars in the past, and that there's been a drop in star formation recently. Now, very briefly, to give you an idea of the model ingredients, because this is otherwise quite boring, so let me go over it quite quickly. So we solve each of these equations where for the stellar mass, we take into account star formation, and we lose mass through stellar mass loss. The same for the gas mass, again, star formation, so through astration, we're going to consume gas. We can gain it through stellar mass loss, and we also account for gas infall and outflows. Very similar again for the metals. We lose it through astration, and we gain it from metals that have been ejected by stars, and gas infall and outflow. But we don't assume gas infall, because we assume all the gas that actually falls into the galaxy is pristine gas. And then exactly the same for the dust. So again, astration, as we've seen before, gas infall, gas outflow. And then here we have the important dust production sources. So first of all, stellar dust production sources, so the AGB stars, and then the more massive stars, which go supernova. Then we have dust destruction and grain growth. And what we want to study with our model is exactly what the contribution is of these last 3 contributions. And again, we assume that no dust falls into the galaxy, so that we have pristine gas infall. Some assumptions on the stellar dust yields and supernova dust yields. There is some difference, of course, in the literature, and I'll come back to that later. So we made some assumptions there, and specifically because we want to model how efficient supernova form dust, we've used the Marassi supernova dust yields, and they do not account yet for reverse shock processing. So what we've done is we've introduced this fudge factor, the F survival, which can vary between any low value up to 1. So this will account for the fact that some of the dust that forms in supernova remnants will be destroyed by the reverse shock and will not make it into the interstellar medium. Then for the grain growth recipe, so the tau grow is corresponding to this time scale for grain growth. And you can tell that it depends, of course, on the efficiency parameters. And typically what people assume is that if you have a lot of molecular gas, you have a lot of dense gas. And in dense gas, the accretion rates will be shorter, so you'll be more efficient at forming grains. And that's why there's the dependence with the star formation rate. So instead of molecular gas, which is not available for all galaxies, in this model, they've plugged in the star formation rate. And then the same for the dust destruction prescription. Again, the timescale for dust destruction is going to be shorter if you have a higher rates of supernovae going off. So this comes directly from the star formation history that we've assumed. Then there's this fudge correction factor, which accounts for the fact that you'll have supernova going off in clusters as well. And then when a first supernova goes off, it's going to destroy dust. But when a second one goes off, actually a lot of the ISM material has been cleared already. Then the free parameter in our model is the MCL, so the mass that has been cleared per supernova. So it's actually a proxy for how efficient supernova shocks will destroy interstellar dust. Then we have some other assumptions. So we have to assume an IMF and as another free parameter. So I told you we have the free parameters highlighted here. So first of all, the F survival, which accounts for the fact or is actually a scaling factor that allows for lower and higher supernova dust production. Then we have a fudge factor, the epsilon, which really scales with the grain growth efficiency. So the higher epsilon, the shorter the grain growth time scale and the more efficient grain growth will be. And the same for dust destruction. There we have the mass cleared per supernova as a free parameter. Again, if that is higher, the time scale for dust destruction will be shorter, indicating that you'll be more efficient at destroying dust. And then we added another free parameter. So those three ones are obvious because we want to try to see what is the balance between supernova dust formation, grain growth, and dust destruction. But we added a fourth free parameter, which is the initial gas mass. Because otherwise, if we fix it beforehand, all of the other parameters will depend on that as well. Because imagine that with our model, we have to reproduce a certain metallicity. If we already assume an initial gas mass, which is, for instance, higher than it actually is, then you'll get a lower metallicity, and then the model will need to make some changes elsewhere to make up for the high initial gas mass. So that's why we prefer to keep it as a free parameter in our model. So what we did then is we actually applied our models to each of these 6 separate evolutionary bins, and we ran 3 different models rather for these 6 bins. So the first 2 models are closed box models. And then for the first one, we've used our customized star formation history, which I've shown before. The second model just assumes the standard delayed star formation history, which people typically assume. And then the third one includes gas infall and gaseous outflows. So the gas infall rate simply scales with star formation rate. And for the gas outflow, we've used this more complex recipe, which accounts for the fact that we assume when a galaxy is less massive, that outflows are going to be more important, while in the recent universe, we expect outflow rates to be somewhat lower. So let me zoom in on some of these results. So in gray, you can see the average or the data points for the galaxies in our sample. Then again, the different colors and the symbols indicate what is like the average value that we get in each galaxy evolutionary bin. And then the different curves represent different Deus models. And what we've done, because they show actually the evolution for over a time period of galaxy lifetime of about 12 gigayear. So what we've done is we've compared the endpoint of these curves with the observed data points. And you can see that actually the correspondence is not that great when we go to the least evolved galaxies, so the black and the purple symbols, and the same when we go to very evolved galaxies. And it's actually relatively easy to understand why that's the case, because especially, for instance, looking at the most evolved galaxies, it's very tricky because, you know, they've recently quenched star formation, they've lost some gas. So we know that our model is going to be very sensitive to the assumptions that we make there. So that's why probably it's not working that well. And the same for the least evolved galaxies. We know that they still have some gas infalls. They have some typically some H1 in the outer parts of the galaxy, which is not contributing to star formation yet, but it will later on. So that's why it's really tricky to reproduce scaling relations for these least evolved and more evolved galaxies. So that's why we preferred to focus on the middle bins, because for those galaxies, we actually know from other studies that there's an equilibrium between the gas that falls into a galaxy that is consumed in star formation, and then the gas that flows out of a galaxy related to feedback related to star formation processes. So that's why we focus on these galaxies, which is also the majority of the galaxies in our sample. Now, specifically looking at the results for one of those galaxy bins that I just discussed. So looking at the 1D posterior probability distribution function, you can tell from the top panel that already the initial gas mass is always relatively well constrained. Looking at the F survival fraction, we find that it ranges between 40 and 90%, which means that quite a lot of the supernova dust that is produced in supernova remnants can actually survive a reverse shock and eventually mix with the ISM. Then grain growth efficiencies are rather low. And we find quite long dust lifetime. So if you remember, before in the introduction, I mentioned that typically people assume that dust destruction is very efficient by supernova shocks and that you get a dust lifetime of about 100, 200 million years. And what we find with our dust destruction efficiencies is that dust lifetimes are actually quite long, so 1 to 2 gigayears, so quite different from what current models tell us. There are a few side notes that I should make. For instance, looking here at the posterior probability distribution function, you can see that it doesn't go down to 0. So for instance, even for the low F survival values, we see that there's still like a probability of 0.4. So we cannot completely rule it out. It's better for the other parameters. But in this case, yeah, it's really indicating that the data that we have are simply not sensitive enough to constrain the models. And then you can also nicely tell when you look at this 2D contour plot, you can see that when you look at the efficiency of grain growth, which is on the x-axis, and the efficiency of dust destruction, that there's like a narrow range of models which we cannot exclude. And it's the models where you actually have a nice balance between grain growth and dust destruction. So you can keep on increasing grain growth, which, as we've seen from the prescription, depends on formation rate. And the same actually for dust destruction, because we assume most of the dust is destroyed by supernova shocks, which again relates directly back to the star formation rate. So that's why there's actually this degeneracy between both parameters. Overall, we found that our rigorous search of parameter space actually suggests an alternative for other models in the literature where they do a simple by eye fitting. So we see that it's actually also possible to reproduce observed galaxy scaling relations when we assume longer dust lifetimes and not very efficient grain growth. So we can also study the relative contributions of stardust and grain growth at each point in time. So the dashed lines correspond to the contribution of stardust, and then the solid lines to the contribution from grain growth. So overall, we see that present-day dust mass has a more or less equal contribution from stardust and grain growth, with some uncertainty, of course. But over a galaxy lifetime, it seems that most of the dust is really produced in stellar sources. Now, a comparison to the literature. So not long after our paper came out, there was a very similar study done for the Dustpedia galaxy sample by Frederick Galliano, and he actually did very similar things. So he also tried reproducing scaling relations, and did also rigorous search using Bayesian fitting techniques. So very similar, although the outcome of his study was quite different. So what he found is actually that he requires very low supernova dust production yields and very high grain growth efficiency. And one of the reasons for this big difference is that the Dustpedia sample and the enlarged sample that he modeled actually does include very low metallicity galaxies. So imagine looking at the plot on the right-hand side, that you really try to reproduce this entire trend of dust to gas mass ratio that steadily goes up and quickly rises when you reach a critical metallicity threshold. So they really go down to low metallicity, while in our sample, we didn't have the low metallicity range covered that well. There's one caveat, of course, in we don't really know very well yet what happens at low metallicity. I mean, we don't know very well how stellar yields depend on metallicity. And for instance, we also don't know how dust destruction efficiencies will vary, because we have fewer metals at lower metallicity. So one thing you could argue for is that it will take a lot longer for a shock to cool down because there are fewer metals present, and you could assume that dust destruction is more efficient, and it could account for part of the relation that we see here. So that's why I think we really need to understand better what's going on at low metallicity, and that partially explains why in the literature there are so many different results. To give you a brief overview of how uncertain supernova dust yields are, as promised. So you see a lot of theoretical models which have calculated supernova dust yields. So the more recent one is from Marassi, 2019, which you can see in red. Then the green curve is the Todini and Ferrara model from 2001. And then the blue solids and blue dotted line is from Bianchi and Schneider, 2007. So the solid one is without accounting for the reverse shock, and the dotted line does account for the reverse shock. Then I've made a comparison. So the rectangular boxes that you can see correspond to observations of galactic and some extragalactic supernova remnants. So the size of the rectangle each time corresponds to the uncertainty that we have on the progenitor mass on the x-axis and the dust yield. So if we try to estimate what a supernova dust mass is in these supernova remnants, you can actually see that they nicely corresponds to some of the model predictions. Now, to give you an idea, so you can see for 3 different papers, so mine from 2020, the one from Frederic Galliano in 2021, and then an earlier work, which I've shown before, by Peter de Vis in 2017, what assumptions were made or what supernova dust yields were found by the models. And you can tell, so the gray curves from my model fall anywhere in between the 2 gray lines on the top, which you can see, while in the models by Frederic Galliano and Peter de Vis, you can see that there's almost 3 orders of magnitude difference. So they assume a significantly lower supernova dust yield. So one way to make progress in the field is definitely try to constrain supernova dust yields better, because it's clear that it's driving a lot of the uncertainty in these models. Now, another paper that was published in 2020 was trying to reproduce scaling relations for low metallicity galaxies and high redshift Lyman break galaxies. And what they actually found was very similar to what we find, even though we fit completely different samples. But what they found is actually they can reproduce scaling relations, such as the one shown here, the specific star formation rate, as a function of dust mass over stellar mass ratio on the right-hand side, without invoking grain growth. So they've included highly efficient galactic outflows and a top-heavy IMF, and they seem to be capable of reproducing the trend as well. So again, this shows that the results that are out there in the literature are really vastly different. And I think the last word really on this topic isn't out yet. Now, the future challenges that I think we need to overcome is that we need to understand how efficient supernova dust destruction is. I've told you that initial estimates assume that dust lifetimes range between 100 to 200 million years, while from the models that I've shown, I actually got more values of around 1 to 2 giga-year, which is a significant difference. Now, from a paper by Felix Priestley, a collaborator of mine in earlier this year, we've actually shown that if you extract the far-infrared sub-millimeter emission, so the dust density of interstellar dust that has been shocked by a supernova shock, and you also have the X-ray observations, then you can constrain what the typical temperature and density in the X-ray emitting component is, and you can calculate from that or estimate what you expect the dust temperature to be that has been shock heated by the X-ray emitting gas. And that's corresponding to the red curve. But what you can see is that there's actually residual emission at longer wavelengths, a cold dust component, which doesn't seem to be heated by the X-ray emitting component. So it's not shock heated at all. And it seemed to be shielded from the shock, which we assume is a cold dust component and where no dust destruction is taking place. So this goes along the same lines that I told you before in the introduction, that we really need to try to see what happens if you have a more clumpy interstellar structure of the interstellar medium and a supernova that goes off and a shock that is expanding in this 3D filamentary structure of the ISM. So I think that's really the future, to try to understand how efficient supernova dust destruction now actually is. Then another important one is whether or not grain growth takes place or not. So I've told you before that there are some challenges when you go to very dense media. You'll form ice mantles, which may prevent from actually elements to still accrete then onto grains, because they'll accrete onto ice mantles. So that's why in a study by Svitlana Sukovska in 2016 and 2018, she started exploring how efficient grain growth could be when you move to a more diffuse medium with densities ranging between 10 and 100 centimeter cube, more or less. And what she found is that if she increases the abundance of small grains significantly, and even lowers the smallest size that you can have for grains, so include really even very, very small grains, and accounts for Coulomb attraction, then you can actually have efficient grain growth also in the diffuse ISM. So you can see the red points or the data points. So in this plot, you see the hydrogen density on the x-axis, and then you see the silicon that is measured in the gas phase. So it's the typical depletion trend. When you go to higher gas density, you see fewer and fewer silicon present in the gas phase, under the assumption that the silicon has gone into dust grains, has been incorporated into dust grains. And you can see with her model, she's able to actually reproduce those trends. Now, there's one important caveat to make there, and this is another paper of a collaborator, Felix Priestley. So what he's done is, because one assumption that was made in the models by Svitlana Sukovska is that actually she didn't assume an evolving grain size distribution, because that makes computations very expensive. But of course, if you have a large abundance of small grains and you're accreting elements onto these small grains, your grains will quickly become larger and your grain size distribution will shift to larger grains. And that's what Felix took into account, which you can see on the left-hand side. So assuming a minimum grain size of 5 nanometer, which is what we typically assume in dust models. And you can see, rather than having the constant size distribution, if you have an evolving size distribution, which is shown in blue, then actually you don't get the strong depletion onto dust grains of silicon when you go to higher densities. You do get it, which you can see in the middle panel, when you indeed include a lot more smaller grains, so going down to 1 nanometer. But we've shown, which you can see on the right-hand side, that actually assuming a minimum grain size of 1 nanometer is not compatible at all with a typical galactic dust extinction curve. So in red, you see a typical galactic dust extinction curve. And if you assume 1 nanometer sized grain, so size distribution that really extends to very small grains, then you simply get too much UV extinction, as you can see. So it's not compatible at all with what we observe. So we think that this scenario of grain growth in the diffuse ISM is not very realistic in the end. So to conclude, so I've shown from this talk today that there's still a lot of work to do in the first place, but that you can also reproduce local scaling relations with high supernova dust yields, with low grain growth efficiencies and long dust lifetimes. So that's a typical picture of very efficient dust destruction and very high elevated levels of grain growth is maybe not a complete picture, and we really need to understand first better how these processes all contribute and what their dependence is on environments as well. So with our models, we've shown that we can actually reproduce local scaling relations where stardust really outweighs grain growth in the ISM over the entire lifetime of a galaxy. And we've done this through doing a first rigorous search of parameter space. And in the future, we do hope to extend it to low metallicity, but then we'll have to change our models a little bit and not just assume a fixed supernova dust yield or fixed dust destruction efficiency, because we know there's also going to be a metal dependence there. Because otherwise, I mean, like in the models that I've shown you before, grain growth is the one relation or one component in all of these models that has a strong metallicity dependence. So if you're then having relations like the dust to gas mass ratio that evolves with metallicity, then of course you'll automatically get grain growth that is going to reproduce that because it has this metallicity dependence. So I hope you learned a little bit more today and that I didn't bore you too much, because I get excited about dust a lot, but not everyone does. And thank you very much for your attention, and yeah, happy to answer some questions.
Thank you very much, Ilse. It's a very complete overview of dust. I think we learned a lot of things today, definitely. There are a few questions. Now I'm gonna show them here. They will appear on the screen. I'll leave you your presentation on just in case you need it to answer the question. So this first question by Professor Denise Rocha Gonçalves. Can you comment on how the Scaly relations discussed would behave instead of H1, the parameter where molecular hydrogen over total mass?
Okay, let me quickly go back. So you mean descaling relations? I think it's a very good point. And for some aspects, the molecular gas mass will be more important. But the one problem is that for some, or for the majority of the sample that we use here, we don't have the molecular gas mass. We did do some calculations how the plots would change when we look at the total gas mass over stellar mass ratio. Overall, the trends don't change. That's one thing, but I do think it's very important, especially in the models. It would help us a lot if, as an extra observational constraint, we would have the molecular gas mass for all the galaxies. Because the problem, as I've shown you before, like in this, let me see, in the typical grain growth recipe, now star formation rate is included, but we actually, it makes more sense to have the molecular gas mass, which gives you an idea of how much dense gas there is present in a galaxy, and doesn't maybe scale always perfectly with the star formation rate. Hope that more or less answers your question.
Okay, thank you. Ilse, let's go to following questions by Jana Martins. So thanks for the excellent presentation. Dr. Looze, can you comment on how the model would change if you consider AGN feedback?
Yes, I think, yes, that's not something that I've included at all. Well, we did consider in the third model gas outflows, but then in the end, for the specific galaxy sample or subsample that we focused on, we know that the outflows really scale with star formation rate. So I think broadly it's definitely important AGN feedback, but I think for the galaxy sample that we're studying, it won't play a role, because we've actually carefully considered whether or not galaxies contain an AGN, and especially because we're fitting the far infrared and submillimeter emission to derive a dust mass. We didn't want to have any contamination from AGN emission or AGN heating, so that's why we actually excluded all of the AGN in our sample, which weren't that many after all. But yeah, just to be on the safe side, we excluded those. So I think it will be important, especially in more massive galaxies, especially when you go back in time. But for the galaxies that we studied right now, it won't have a strong impact.
Okay, thank you. So we have some other comments on the way. Amanda Carvalho is saying, great talk, Dr. Looze, thank you.
Thank you very much.
Follows it. So question about dust. She says dust rules the universe.
Completely agree.
Denise is saying that you answered her question, and again she thanks you for a very nice and complete talk.
Thank you very much.
Jana as well. I have a couple of questions. I mean, I'll take advantage. We have just a few minutes. The first is a very general question. You mentioned at the beginning of the talk that from studies of Cassiopeia, the 70% of the dust is destroyed by supernova, right? This probably applies to the other nearby supernova studied. And how this coincide with the role that supernova have in enriching in the very early universe, the ISM. I mean, is this picture with this high rate of destruction, does it work fine? I mean, you didn't. It's not part of it all, but maybe I'm sure you've seen this.
No, it's a really good question. I've just shown you the example of Cassiopeia A, but for instance, the other supernova remnant shown there, the Crab Nebula, doesn't have a reverse shock. So to have a reverse shock, you really need to have quite a dense circumstellar or interstellar medium. So you really get a rebound of the forward shock, and it rebounds so that you get a reverse shock propagating inwards. And I think at the moment we have not such a clear idea of what the fraction of supernova remnants is that actually experiences a reverse shock. So we know for Cassiopeia it's very prominent, but we may also be biased towards supernova remnants where there's reverse shock processing, because it makes them stand out. You have the reverse shock that is heating a lot of the ejecta and the dust in it. So it really stands out from typical interstellar dust temperatures, and that's why we easily pick up on them. Because the problem is, if you go to supernova remnants, which don't have any shock processing going on, we expect supernova dust to have already cooled down significantly, and we may just not be able to pick it up. I mean, if you look in our galaxy, you have a lot of interstellar material along the line of sight. And then to come back to your other question, I mean, it's not something that I've studied before, but there are now, well, it's more for the supernova dust destruction by the forward shock, but there are some arguments that at high redshift, maybe if you have a dense circumstellar shell, it may prevent the forward shock to actually propagate into the interstellar medium. And that's something that I know some people are investigating right now to try to see whether that could be one aspect why maybe just in general, dust destruction in the interstellar medium is lower. And that could also apply then to high redshift.
Okay, thank you very much. Let me see if there are any other questions. Nope. Can I ask one more thing? Do you have a couple of minutes?
Yeah, no, it's fine.
In the plot that you showed by Galliano, along metallicity, there is this huge difference between dense Lyman alpha systems and dwarf galaxies. I was expecting that then Lyman alpha were kind of similar population at high redshift. I mean, from the dwarfs that we know in the local universe. Did you know what is this? How are they so dust rich? I mean, and therefore metal rich compared to more normal dwarf galaxies?
Yeah. So people don't know yet whether it's a real difference or whether it's an observational bias. Because, for instance, looking at the nearby universe, or for the nearby galaxies shown in blue here, we know that a lot of them have a very extended H1 disk that extends beyond the optical disk where we see the stars. So that may be one aspect that brings maybe the dust to gas mass ratio down for some of the very low metallicity galaxies. On the other hand, for the damped Lyman alpha systems, they don't have the dust measurements from looking at the dust spectral energy distribution. So they don't have typically the far infrared 2 millimeter emission. They rather look at elemental abundances and depletion trends. And then they use the assumption that zinc is not very depleted at all, so that it's mostly present in the gas phase, and then compare that to other elements to get a sense of what the level of depletion is of elements on dust grains and get a dust mass out of that. But there have been some recent arguments, that's may tell us that that's actually not a accurate thing to do. So maybe that's something we'll need to revisit, and that may shift the position of the damp Lyman alpha systems. Because for now, it definitely it remains a puzzle why they're so different. Because it seems that the damp Lyman alpha systems almost follow a linear trend, and in that sense, I mean, it just linearly scales with metallicity. Then it would be consistent with stellar sources, because the stellar sources produce all the metals. And then if you always have a fraction that is locked up into dust grains, then you could assume a simple linear relation. So I think, that's definitely something that people are interested in, to try to figure out why it's so different.
Okay, thank you. I don't think that there are any other questions. But do you plan? So you didn't study yet dwarf galaxies. Do you plan to extend your? What's this? I mean, dwarf galaxies are so important. I mean, you can't leave them aside.
Yeah, it's true. No, I mean, I think we definitely should, but on some aspects, I'm not sure yet what to assume. Because the problem with maybe Frederick Galliano's studies, and I'm not saying that my study didn't have any problems. For sure, some of the assumptions that go in there is just because, we know too little about how grain growth actually takes place. But I think we really need to understand how dust destruction efficiencies and for instance, stellar and supernova dust yields scale with metallicity. I would be excited to extend it to low metallicity galaxies as well, for sure. Yeah.
Okay, listen. I think yes. No, there's no more questions. So I'm gonna take a chance to thank you once again for accepting the invitation, for giving this very good talk, and so I hope to see you sometime in Europe sometime. Okay.
That would be great.
Thank you very much. Take care.
Yes, thank you very much. It was really nice. No, I would prefer being there, but yes, I guess in a post-COVID time.
Well, yes, it's a time we can organize another seminar at the same time here.
That sounds good.
Okay. So thank you all. I will see you next Tuesday. And bye-bye, Ilse, once again. Thank you very much.
Thank you. Bye-bye, everyone.